This is section 4.7 now, and we're going to talk about the simplification of a system of forces. We're going to come up with a system resultant. Okay, let's say we have a random object here. We're going to apply a force going in this direction. And now let's apply an equal opposite collinear force going in this direction. In other words, the same magnitude, however the force is opposite. And if they are collinear, that means they're lined up. Would you agree that there is no net effect? I hope so. The same thing would be if I pulled a force in that direction and I had applied another pulling force in that direction. If they're lined up, collinear, there would be no net effect. And we call that no net effect by sum of the forces equal to 0, like that. We also know that because they are not separated by any distance, the sum of the moments are going to be equal to 0 as well. How about if I apply a couple? Let's put a couple here onto this random object. We're going to say I'm going to have a force and another force separated by a distance. That's clearly going to have a couple moment going in this direction, in the counterclockwise direction. Let's put now an equal opposite couple. I'm going to say that the force is half the magnitude, but separated by twice the distance, and I would have the same equal opposite couple, in this case going in the clockwise direction. There would be no net effect because this couple is going to be equal and opposite of this couple. Now remember that couples are free vectors and they can be applied any place on the body. In other words, they could be here or here, any place, they'll have the same effect. Couples have no net force, however, so the sum of the force is equal to 0 from couples. Now let's talk about how to replace a system of forces with a force couple equivalent system. So we have a force being applied at the end of this beam, and we may want to know the moment about point O. Well, the moment about point O is force times distance. I think we can know that. But let's see if we want to simplify that a little bit. If I were to apply a force here and here of the same magnitude, wouldn't you agree that there'd be no net effect caused by those two forces? However, this force and this force are now a couple, separated by that distance, and I can replace that force and that distance with a couple, leaving the force here and the couple. So in other words, this system here is equivalent to this, and this system is equivalent to that. You can replace those forces equal opposite like that, and replace them with couples. And we know that some of the forces are going to be equal to the same. Some of the forces here are going to be equal to minus F. Some of the moments is going to be equal to minus F times distance in all three systems. This also works with multiple forces. So let's see if I have 2 or 3 forces here. I'm going to use just a 2-force system. I'm going to say that I have a force times that distance and that force times this total distance. That would be equal to the moment about point O. These two forces can be replaced with a third force. In other words, sum of the forces is equal to a resultant force. This distance may be unknown, but however, that force can be replaced by, or this, I can add the same magnitude of force right here, separated by that distance, and then these two forces by that distance can be replaced by this couple. So in other words, this system here is equivalent to that, which is equivalent to this one, which is now equivalent to this one. So this is the principle of simplification, replacing a system of forces and couples with a simpler system which has the same net external effect. In other words, before equals after. And that's kind of the system and the principle we'll be using as we go forward. Well, let's look at this one then. This has a system here. We've got several forces. I have a 40 Newton force being applied, 30 Newton of force being applied, a 50 Newton at an angle, and this is a couple that we'll be applying it to the beam as well. And we want to replace this loading system with an equivalent force couple system acting at A. So the first thing we want to do is come up with a resultant force of these three forces. So let me put the components of this force here. I know that there's going to be a force in this direction and a force in that direction. And if this is 50, I know that this one is going to be 3/5 of 50. And this one will be 4/5 of 50. In other words, that's 40 pounds. Newtons, I'm sorry, 40 newtons. Let's come up with the resultant force before we do any simplification. So the resultant force is going to be equal to negative 40 J, negative 30 J, negative 3/5 of 50, so that would be also 30 J, plus that 4/5 of 50 in the I direction, so that would be 40 I. And we can add all those together, and we can see that the resultant force would be 40 I minus 100 J. And that's going to be the resultant force. Okay, let's put a little red box around there. Okay, how about the moment before? The moment before is going to be, again, we need a point of rotation, so if we have point A, this force will cause no moment, but this one will have this lever arm, this one will have this lever arm, this one goes through the point of rotation, and then this is a free vector that we'll be adding in there. So if I add the moment before, it's going to be equal to the moment about A, positive going in that direction, be negative 40 times the distance of 0, negative 30 times 3, negative 30 times 6, and then the 40 would be also, I'll call it with a lever arm of 0, but then we also have that negative 200. That's also going in the counterclockwise direction. So I'm going to add all those together, and I'll say the moment before is going to be equal to minus 470 Newton meters. Okay, how do I replace that with an equivalent force coupled system at A? Let's go ahead and move this up just a little bit. I'm just going to do that. Okay. So what I want to redo or draw is this system again. So I'll draw it like this. And what I want to do is say that I'm going to replace this point A with this force. I'll say that it looks like that. This is the resultant force. It's going to be equal to 40I minus 100J. And it will have an equivalent couple, or the resultant couple will also be going in that direction. And don't have to do it. If I draw it in the negative clockwise direction, then I shouldn't put a negative sign on there. So this will be my equivalent force couple system at A. Well, F427 is another fundamental problem, and here it's saying replace this loading system by a resultant force acting, or resultant couples and moment. Resultant force and couple system acting at point A. So a similar kind of thing where there's going to be a cosine component and a sine component, 30 Newton, and I got this was going to be a positive. I find the resultant force is 450I minus 1079J, the moment before. This cosine component will have a lever arm. This will have this lever arm, and then this will be a positive going the other direction. So this will be the this will be the total moment about point A, and we can replace that. That looks like that, the same kind of thing. What I want to do is use this problem and say, well, what about point B? In other words, if I were to say what's the equivalent force couple system about B, I could do that as well. So let's go to the next page. And here we have the same problem, except that we're going to do the moment about point B, or we're going to try to find an equivalent force couple system acting at B. The resultant force is going to be the same. However, the moment before, when I do this force goes through B. This is going to be the lever arm for this one, so it'll be 300 times this lever arm going in the negative direction, adding the 300 to that direction, or adding the 300 in, I get a total moment before is equal to 150. So in this case I have the resultant, which is that, and then I have a negative 150 moment going in that direction. Here's going to be my equivalent system. Well, what we have here is a series of parallel forces. They're all pointing in the negative J direction, and they can be replaced with a single force, a resultant force, separated by a distance. So let's go ahead and draw that in there. I'm going to say that there's a resultant force here, some R, and there's going to be some distance from that reference point that they can be replaced by. So let's go ahead and find out what our forces are. First of all, let's say that the resultant, let's look at our before condition. So the before condition is the resultant is going to be equal to negative 500, negative 1000, negative 500, negative 2000, and negative 500 in the J direction. So those are all considered, or all together is going to be negative 4500 J. That's going to be equal to the resultant. Now what is the effect of that in terms of the moment? So the moment, point A, positive going in this direction. Again, this one, this 500 has no lever arm, but this 1000 has this lever arm, the 500 has this lever arm, and so on. So those are all going to be negative for this point in time. So I'll say the moment about A before is going to be equal to 500 times 0 minus 1000 times 1 minus 500 times 2 minus 2000 times 3 minus 500 times 4, and we get a resultant moment is equal to negative 10,000 Newton meters. Okay, so that is our before condition. What we want to do is replace, find out what the after condition is, and let's go ahead and write that out. Let me scoop this up just a little bit. All right, my after condition looks like this. After, what we're going to have is this resultant separated by that distance, and we're looking for something that's going to cause the same effect. So all I have to do is say that the moment about A after is also going to be equal to the resultant times the distance. I know the magnitude of that moment that I'm looking for is equal to negative 10,000. I know that my magnitude of the resultant, so the distance is going to be equal to 10,000 divided by 4,500, and I can find that distance is equal to 2.22 meters. So that is the distance at which I would place my resultant in order to have the same effect. In this case, there's no residual moment because this resultant placed at this distance will have the same effect as my original conditions. Well, the next type of problem I want to cover is where we have forces coming from multiple directions. And what we're looking for ultimately is to find out where the resultant can be applied at some place along this line such that the effect is going to be the same as all of these forces acting independently. What I'm going to add here, just for a little bit of interest, is I'm going to add a couple moment here of 2 kilonewton meters, and you'll see how that comes into play here in a little bit. Alright, let's find out what the resultant before is, before I do any moving. So let me go ahead and put the components of this 5 kilonewton force up here. And this is going to be the 4/5 component in the y direction, so that would be 4 kilonewtons, and this is the 3/5 component, so this is 3 kilonewtons there. Alright, let's find the resultant. Sum of the forces is going to be equal to the resultant, so I got negative 8I, negative 6J, negative 4J, and then positive 3I, and that gives me the resultant there. The effect of those forces about point A is going to be moment, so I have this 8 times this lever arm going in the positive direction, 6 times this lever arm is going in the negative direction, 4 times this lever arm, negative, and then 3 times this big lever arm is also going in the negative direction. Then I have this 2 in the positive direction. Adding all those up, I got the moment about A is 3 kilonewton meters in the positive direction, positive there. So let's go ahead and write or draw that into the draw that onto the picture. I'll just do it here. I'll say that this is the resultant, and it will also have a moment there of 3 kilonewtons, 3 kilonewton meters, and the resultant here is equal to negative 5i, negative 10j. Okay, now that's only part way there. What I want to do is find out, is there a place on this axis where I can apply this resultant and not have to do this and still get the same effect about point A. So I want to draw that resultant like this and see if I can find this distance d, and if I could just apply that resultant alone, can it have the same effect about point A? Well, the way we're going to look at that is if the resultant has components in this direction, where this is going to be 5 in the I direction and this is 10 in the j direction, what we can see is that if I move that resultant up the line here, only the 5 component has a lever arm. The 10 component goes right through the point of rotation, point A. So all I have to do is find out this distance d here, where this 5 times that distance equals the same moment that we had before. Alright, so let's go ahead and scooch this up a little bit, and you can see the way I did that. I'll keep that right there. So only the 5 component, the 5I force, has moment about there. The 10J goes right through A. So the moment is equal to 3. It is equal to 5 times D, and you can solve that for D as 0.6. So that concludes our simplification process for now. And what we'll be adding in a little bit are distributed forces. But for now, this is where we're at.